Hello, today we are going to talk about the first three inferential statistical tests that you're going to learn in this course. And they are all about comparing observations to expectations. Or, as the title of this video says, they are also thought of as tests of goodness of fit. So, how does this work? Well, so we're making inferences here. We're making observations, and if they are close enough to the expectations that we have set up in our hypothesis, then that is evidence that our suspected process that we've described in our hypothesis is what's going on. So we have to suggest a real-world phenomenon that's causing things to happen the way they are, and that's our hypothesis. And then we use our combination of what we know about statistics and what we know about the specific field that we're studying to choose a random process that seems like a reasonable explanation for the noise or the unknown aspects of what we might measure. And that process will have a probability distribution that then we can use to quantify how well our expectations fit our observations. And the idea here is that we're going to hope that if we know what's going on and if we've correctly predicted what's going on, then any noise or error or variation in our measurements or our outcomes that we see are simply going to be due to the randomness that we expect from this probability distribution, and not because of some other systematic things that are more than what we'd expect from the probability distribution. So because we have described what we expect in terms of a probability distribution, and because that probability distribution gives us a way to quantify just how probable any particular observation is, we can say exactly what the chances are of observing the test statistic given the probability distribution that we're expecting. So, average car speed on Sheridan Road, and average concessions purchased to a per attendee target. So those are continuous examples. And a discrete example would be if Coke has a 60% market share, does our sample of 100 soda drinkers have 60 Cokes? I probably should capitalize that C. Anyway. So basically what we're doing is we're converting this, we're going to find some measure of how far away our observations are from expectations, and then we're going to convert that into a probability. And if the probability is low enough, then we say that it's not likely that our description of what's going on is true, and that we have to reject it. So the continuous processes have two different random processes that we use to quantify how far. If we are drawing our sample from what we think is a population with a known mean and a known standard deviation, then we use a z-test. And almost the only way you're going to ever encounter this in the real world is if you're working with seeing if a sample of people comes from the global sample of like a standardized test. If the population's mean is known, but the standard deviation isn't, and that is much more likely in the real world where you have some quantity that you expect the population to be near, but you don't know how spread out it's going to be, then you can use a single sample t-test. The single sample t-test of comparing an observation to an expected mean value is going to be one of the most common things we use in this course. Finally, one of the most useful statistical tests you will find in stats is the chi-squared test of goodness of fit. And that's when you have a discrete variable. You count how many times your observations fall into each possible category, and then you compare your actual observed frequencies to the expected number of frequencies for each category. And you can estimate the probability of observing your sample if your expectations are correct. One last thing that's useful, both for z-tests and for t-tests, is that when we're talking about how far, we have to measure it not just in terms of how variable the distribution is, which is the standard deviation up here, but also the sample size, which is n. So the standard error of a mean is the square root of the variance divided by the sample size, or alternatively, the standard deviation divided by the square root of the sample size. And that is a really useful measure of how confident we are in the mean that we've estimated. So a small standard error means that we have a pretty confident estimate in our mean, and a large standard error suggests that there's a lot of uncertainty about how accurate our estimate of the mean is. think that will do it for the overview. No, it won't. There's one more slide. I worked a lot on this slide, actually, hilariously, and I almost forgot it. So here is kind of a cheat sheet slide for you. So we have the 3 tests of goodness of fit. We have the parameters that your test uses. We have the sample statistics that are calculated. So I should say, I should actually change that to, let me do that right now. Come on, double click. Work with me here. There we go. Statistics calculated. Glorious. Back to presenting. So we have to compute the sample mean and the standard error of the population mean for the z-test, the sample mean and the sample standard deviation, and the standard error of the sample mean for the single sample t-test, and we have to compute chi-squared values for each group and the total chi-squared value when we are computing a chi-squared test of goodness of fit. Then remember, the null hypothesis is actually the thing we're trying to reject, and it is the thing that describes what we don't think is happening. And then the inference is what we believe or hoping is happening based on the maximum likelihood estimate.